rest assured that I don't think any of this will be on the final. But as I hope I can convince you over the course of this lecture, some of the things that you could learn from this could be very useful for you in a variety of different domains. So food for thought. So what am I going to talk about today? First, I'm going to do a bit of a recap on what you guys learned last time with regards to object detection neural networks, some of the very cool applications of the data science techniques that you've been learning in this course using the canonical YOLO neural network for object detection, and use that to motivate some of the techniques that we'll discuss today, which have to do with so-called synthetic image data generation, which, as I'll try and convince you, is a bit of a different way of looking at data than maybe you've been exposed to in the course thus far, and try and keep it fun with a bit of a demo, where I'll show you how to not only use data, but also generate it yourself if you need more of it, and then conclude with some remaining challenges and future outlook. So recap, object detection, as you learned from Will last time, the goal here is you have an image, an array of pixels, and you're trying to detect objects, a high-level understanding of where, in this case, people are, or speaking of bicycles or road signs. Locating and classifying objects in an image with a huge number of different applications. This one may be pointing towards autonomous vehicles. Identifying in this image where the objects are with a bounding box, with a width and a height and a centroid, and then also predicting what class that bounding box belongs to. And so I think you guys took a look at some tennis examples here. What I want to highlight is this data pipeline, which you learned that the first step is really collecting data, and lots of data. As you know, you need lots of data to train these neural networks, and then you need to often manually label that data, and huge amounts of it to get state-of-the-art performance. And you learned about some annotation tools to do that. I'll actually show you one in a second as well. Who are these data labelers? How are they paid? How are they employed? Maybe you've heard that there are a bit of ethical questions regarding that, which will really motivate what we talk about in this lecture. And then some more advanced methods for doing data labeling automatically. And then I won't touch on this because this is, of course, a huge topic for not only one other course but many other courses. But you learned about the basics of training models with this data, iteratively. Not only training once, but training many times when you realize that your predictions might not be quite what you want them to be. And I'm going to quickly run through this as well, but yeah, ultimately we want to make predictions, and you learned about these heat maps to understand where these predictions are in the image. And specifically, you learned about a particular object detection model, which I mentioned, YOLO, which has many versions, but definitely has achieved state-of-the-art performance on many tasks for real-time object detection. First introduced in 2015, and most recently has been updated by Ultralytics. And what I want to highlight, though, is the challenge here, which is the quantity of data that we need for these models, and how we can maybe improve this pipeline. So just to give you a sense of how manual and tedious this is, what does a data labeler do? I'm going to really quickly show you. So this being an example, let's say you wanted to detect this object. And I know this is tedious, but that's the point, is you often have data labelers pulling up these images, and then they have to manually, with a cursor, label and very accurately label where is the beginning of the bounding box, where is the end of the bounding box, what is the class that this object belongs to, and ultimately do that for every single image that you need for your data set. And you can imagine that this is not scalable for a number of reasons, or it is scalable if you have enough people. But the problem being, if you have a new data set that you need to label, or you have objects with a variety of different features or manifestations in the real world, that this can get to be very time-consuming, and there is great potential for error in how you're exactly drawing these bounding boxes. And so the question is there a better way to do this, a more automated way to do this? And so that's what we'll talk about now. First of all, any questions on that? Mainly recap, but happy to answer any questions about that before we go on. But if not, we can get to the more interesting stuff, which is this idea of data-centric AI. And maybe some of you have heard this term, which was coined by Andrew Yang in a talk a few years ago, where he pointed out that in an ML workflow, 80% of the time might be spent on data preparation, and only 20% on, he used a cooking analogy, on cooking the meal, that is training the model. But the research in AI seemed to be 99% on the model-centric side and less than 1% on the data-centric side, which involves sourcing and preparing high-quality data. He defined data-centric AI as the discipline of systematically engineering the data used to build an AI system. So can we think a little bit more about that 80% as opposed to just the 20%? And this is where this concept of synthetic data comes in, which maybe some of you have heard of. The idea of not only using real-world collected and labeled and annotated data, but actually coming up with pipelines that can do that synthetically, that is computationally. So on the left here, this is a lot of academic work has gone into this, but I think I'll try and convince you that there are quite a few industrial partners, a lot of industrial interest in commercializing this as well. But academically, a lot of research on it. On the left, what you just saw, where we're collecting data, we're cleaning it, annotating it, reviewing, auditing it, using it to train the model, evaluating, and then oftentimes we have to do this iteratively if our model is not performing to our satisfaction, and that's quite time-consuming. And so the synthetic approach is instead summarized on the right, where instead, in the context of computer vision, which we'll focus on here, we're instead going to build an environment which we can use to automatically generate this data and do so parametrically as opposed to manually. And there are advantages to doing this as opposed to just reducing manual labor. Another advantage being the quality of the data itself is quite a bit higher, because there's a variety of different ways that we're tasks that we're trying to perform with this data shown on the left, whether it's doing as I talked about before, bounding box labeling, as we have an image and we want to know where, for instance, a chair is or a table. In this synthetic approach, as I'll show you, our annotations are pixel perfect. There's no errors as a result of human labor incorrectly drawing those bounding boxes, whether they're in 2D or in 3D, if you want to do 3D scene understanding, which is important for instance, autonomous vehicles, or even more complex tasks, which are, quite frankly, almost impossible or very unscalable with traditional manual labeling, like instance segmentation, where we're not only trying to draw bounding boxes, but imagine trying to draw a mask around all of the pixels for the chairs, in this case, either individually or collected as a class. That can get extremely time-consuming, as you'd imagine. Or even for even more complex tasks, like estimating key points for pose estimation. So what we're going to try and do is generate a synthetic data pipeline that can automatically produce these pixel-perfect annotations and output them in the data format that we need to train, for instance, a model like YOLO. And as I said before, not just for computer vision, but we'll focus on it here. Another advantage is, as you've learned, overfitting is a problem. Is a big problem. If you don't have data that is diverse enough, then your model can overfit. And the advantage here is that we can generate not only a lot of data, but a lot of diverse data that has, shown on the left, kind of a histogram. We have a certain number of classes, and instead of having, for instance, class imbalance, where we have too much data of one class and not enough of another, we can generate what distributions we want. Or in the histogram shown on the right, in some of the images that I'll show you in a bit, a really wide variety of data. So what does this actually look like? And this is one such image, which looks kind of strange. Can you all see it a bit? It's a bit dark. It's a bit dark, but maybe you can see that this is an image with a bunch of objects in it that look somewhat photorealistic, but the backgrounds definitely don't look very realistic. Looks like some Amazonian jungle almost that these random Triscuit boxes and cereal boxes are placed in. The point being that photorealism in these synthetic data generation pipelines is important. Diversity of the data is so-called domain randomization to try and train the model to recognize as many different features as possible is just as, if not even more important. I won't go through this too much, but just to say that in academic research, it's been found that these pipelines can achieve state-of-the-art performance on par with real-world data by metrics such as the ones that I'm summarizing here, where for the case of the bounding box detection that you learned about last week, we're considering how close is the predicted bounding box to the ground truth by this metric intersection over union, which I think will make a bit more sense when we do the demo in a bit, where we're trying to find the overlap between our prediction and the ground truth, and doing that for one or potentially multiple different classes that we're considering. And this is a bit of a table underneath, but just to show that what researchers do often is they compare, well, what's the performance of the model on real-world data? That's shown here, baseline. And notice the number being quite low relative to how much synthetic data you can produce. But the MAP, the mean average precision, which is often used to evaluate the performance of these models, is in this example 0.45. What the researchers find is if you use purely synthetic data, that is purely data generated and labeled in the computer, the performance is not quite as good for some of the reasons that I'll talk about in a bit. But when you combine these two, a large amount of synthetic data, like the data that we'll generate in a second, along with real-world data, that you can improve the performance of these models sometimes quite significantly by a variety of metrics. 400,000 data points as opposed to 760. So the scale is orders of magnitude. And it's not just academic. There's companies which increasingly are trying to commercialize, especially these days, with the demand for such data. Only 3 of which are listed here. One of the most challenging areas being human face detection, as you might imagine, is, as you'll see in the graphics engine that we'll play around with to generate this data. Getting human facial features right is very hard, as you can imagine. Maybe one of the more developed applications being autonomous vehicles, where these virtual scenes can render, and then, as this image is kind of alluding to, segment the instances of cars or bicycles or street signs. So it's not just an academic interest. There's commercial interest as well. And so we're gonna play around with it ourselves. Before I go on, any other questions? Any other questions about any of this? Yeah, sure. Let's see. You'll probably be exposed to data in the real world that is not exactly what you're training on. I think that's the main reason. Is you're right. If you have this algorithm that takes an image and creates that bounding box, it's kind of cheating, because in that case you know in your virtual scene where exactly the object is, whereas in the real world you don't. But it's a good point. Yeah. Does that make sense at a high level? Yeah. I guess the advantage being that in this virtual world, you know everything. As we'll see in a second in the demo, you know exactly where the objects are quantitatively. It's not just images you have all this other information in this virtual scene. Whereas in the real world, if you have a camera on your autonomous vehicle, you just get the RGB image, and that's it. Yeah. Good question, though. Any other questions before I go on? All right. So I just touched on some of the commercial tools that companies are developing to do this. But good news is that there's a lot of open source, freely available tools as well, which means that individuals who are hoping to train their own custom neural networks, such as YOLO, which I definitely encourage you all to do. It's amazing how many tutorials, freely available resources online there are to do this. to train the models, but also, as I think I'll hope to convince you in a second, to generate the data to do so. So let's say you have a certain object detection task that you want to do that's not just to detect a dog or to detect a cat, such as the YOLO model pre-trained can do. What if you have certain images that you want to detect objects in that are particular for your custom application? These are just a few of the environments that folks use to generate the sorts of virtual worlds to generate that data. Maybe you've heard of some of them. Unity, Unreal Engine being maybe the most graphics intensive, and then some of the less graphics intensive being SketchUp, for instance. But one of the most versatile and flexible, and one that has the biggest open source community is actually something called Blender, which is a 3D animation rendering modeling software. One of the big advantages of Blender is that it has a tremendous Python API. And so all the skills that you all have been developing in this course in learning how to script in Python can not only help in inspecting the data, analyzing the data, or training models with the data, but also, as I will try and show you in a second, for generating synthetic data to begin with. And so let's dive into a bit of a demo. And this will be a bit of a crash course in, first of all, how to use this software. So bear with me for a second. But this is Blender. This is one of those tools that people use to create these virtual worlds. Again, the lighting's a bit off, but can you all see a bit? Can you see it all right? Okay. So for those of you who've done computer-aided design or CAD, it might look a bit familiar. For those of you who have not, it might look a bit overwhelming, but bear with me as I just walk you through the UI for a second. Over here is the 3D scene, or the 3D viewport. And it can be either rendered, as I'm showing you here, or not. Maybe I'll start with the not rendered. It's a bit simpler, where we have this X, Y, and Z spatial coordinate system. And we have, in this case, let's say, to keep the example of the headphones, we have these, I think they're AirPods. The X, Y coordinate system shown here. In addition to just the object, we also have some other elements in the scene, like some lighting, which will become more apparent in a second, which we use to render the actual. Can you? Oh man, it's so dark. Can we dim the lights maybe a little bit? Would that help? Light switches are behind. Okay. Nope. 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 Is that any better? That's one of the lights that I'm pointing at, but if I could dim the real lights in this scene, then that would be nice as well. Would this be it? Or would that be? This one? Oh, that's better. Oh, okay. I hope you all don't fall asleep, but anyway. Yeah, other elements in the scene that are important in addition to just the object that you want to detect are lights, which will be used for rendering, along with cameras. And these cameras are actually what produce the 2D images that we'll use to generate the synthetic data. So ultimately, this is the sort of image that we'll get. Not that though, because when we render it, it'll look a bit more photorealistic. And we can change the angle that we're looking at the object, for instance, or we can rotate the object, or we can move the object in different ways. What I'm showing you there is manipulating the virtual scene manually, but as I said before, the whole point of this is we want to do it programmatically. And so that's why on the right here we have the scripting interface. So using Python, using the same language that you all have been learning over the course of this semester to do what I said was very important for this method before, which is domain randomization, so-called, which is creating data that is very high diversity. And how would you imagine? Here, the quiz question. How do you think you would randomize image data? What methods do you think? What do you think you need to do to generate enough diverse data that you could train a neural network to recognize the objects in the real world, where you might not be able to anticipate different different conditions. Yes? Yeah, change the lighting, absolutely. So you can control, for instance, the luminosity of those, not only the luminosity of one light, but how many different lights you have, their position with respect to the object. That's definitely very important. That's definitely very important, yeah. Any other ideas? Yes? Yes, exactly. And there's two ways you can do that. You can either change the orientation of the camera, or you can change the pose, the position, and orientation of the object itself, or multiple objects. Yep, absolutely. Let's see. There's a lot more, but there's one more that we'll touch on. Any other guesses before I give it away? Yeah. How else could you randomize elements of an image that you need to synthetically generate to anticipate what the real world scene will look at, in addition to lighting, in addition to orientation? Let's let someone else have a shot. Starts with an M. Didn't start with an M. The last one being the material texture. So the advantage of these photorealistic rendering pipelines is you can generate very, very true-to-life looking materials, which have a big impact on the color, the texture of the final object in the image. And so let's, this is a bit, I know this is a bit of a different environment than what you all are used to scripting in, but hopefully the syntax will look a bit different. And as a reminder, none of this will be on the final exam, so don't worry. What I'll show you here is a few scripts that maybe I'll start with the simplest one, that you can write to automate the generation of images in the correct format for instance, YOLO, in this sort of environment. And so maybe I'll walk you through a few of them. Can you see all right? Is it big enough? I think it's a bit, the text is a bit small. Let me try and okay. So, just as if you were in a Jupyter notebook, you need to import various libraries for this. Maybe some of which might be familiar to you, some of which may not be. Math, OS operating system, NumPy as well, and the big one that's definitely not familiar to you probably is that one that's called BPY, which stands for Blender Python. So that's the library that allows you to manipulate the virtual world with a Python scripting interface. And then some others for image processing that we'll touch on in a second. But here I'm defining two functions that will do one of the domain randomization techniques that we just mentioned, which is randomizing the camera orientation, position and orientation. And so the first one, randomized camera, takes in two arguments: a camera, which will be a reference to the camera that we've set up in the scene that I just showed you, along with the object that we want to render. And then it's going to take that, and it's going to take various attributes of that camera, the position, X, Y, Z, and perturb them, kind of jitter them a bit. And I'll show you what that looks like visually in a second. So again, this box being the 640 by 480 pixel dimensions that are required for the YOLO training model. And what we're going to do now is hopefully run this script. And what you see is every time I run this script, what we're doing is we're calling this function, which jitters the camera parameters, and can do this obviously iteratively. And every time we do that, you can get a bit dizzy looking at this, but we get a different view of the object from a different angle with a different background. I think this is a background of an Apple store, fitting. Which is important. You want the distribution of the synthetic data to match as much as possible the distribution of the real data. That's important. And so it is good to have photorealism not only with respect to the object, but also the background. So you can see that we were just looking at the viewport from the camera itself, but maybe you can also see here's the camera that we're rendering the image from, that we're generating our data from. And you can see how every time we run this script, where did the camera go? It went somewhere. I'll try and find it again. There it is. So this little icon describes where the camera is in the world and what orientation it's looking at the object in. So now it's over there. And the second function that I have is to ensure that whenever we move the camera, it still is looking at the object, which touches on one of the challenges in these pipelines is making sure that you're setting up the virtual environment to generate good data, because it's very easy to set up a virtual environment that will generate bad data. Obviously won't help you. And so the second function being one of these helper functions that will take that camera object and ensure that it's rendering an image that is actually looking at the object, because having a bunch of images that don't include your object that you want to detect is not going to be very useful. So for instance, in this case, it takes that camera and sets its position. There's some spatial coordinate transformations going on here, but at a high level, what it's doing is it's just aligning the camera with respect to the in the world frame such that it's pointing right at the object, which the object itself called headphones. So this library being the one that we imported up there, from this library you can get all the data in the virtual environment, and from that data you can get certain objects, and the objects are actually listed up there. If I didn't shrink the window enough. And so you can get references to all those objects in the virtual world, and you get reference to the camera and then the headphones, and then use that to do the randomization. Does that make sense at a high level for everyone, or does anyone have any questions about how we're generating data in this way? Yeah, sure.
Do everything with this image, right?
Yes.
Say you had in the real world an image of a headphone on a person.
Yes.
You'd have to train your model to also work with that, right? You need to do the same process.
That's correct. Yeah, it's a good point, which is that this is a simplified example for a first go, but in the real world, you would want to have an environmental context that is as realistic as possible. So in that case, it is important to, and actually that touches on another advantage of synthetic data that I didn't mention before, which is privacy and anonymity. Actually, one of the major problems that sometimes companies have is they're trying to use data about humans or about faces, but if you're using real data, then there can be privacy concerns. I think there was a famous example with, what was with the celebrities? There was a group of celebrities that got very up in arms, rightly, about the fact that their data was being used without their consent. So, with the caveat being that it's challenging to generate photorealistic images of humans and of human faces, if you can do that, then you don't have the same privacy concerns that you do with other real-world human data. But you're right, that's definitely necessary in this context. Yeah. Good question. Any other questions before I move on? Any guesses where this scene is, by the way, that I'm rendering here? I know it looks a bit distorted, like a fisheye view. Anyone been to this very obvious looking location? This is Apple Park. It's Cupertino. So, all right. Let's see. Let's try randomizing the lighting as well. So the first suggestion was we have these lights which can have an impact on the appearance, on the final appearance of the object. Here's a different script, same libraries as before, but here we've written a function, randomized lighting, which takes in a light or multiple lights, and is going to also, in a similar manner as before, it can jitter their position, which ultimately, in this virtual scene, they're sending out rays of light, which are then bouncing off the object and then hitting the camera, which determines how they're rendered. So we can change the position of the lights to get some domain randomization. We can also, as was alluded to before, we can change their luminosity or their power to change the brightness or the darkness of their reflection off of the object. And so that's what we're doing here. We have this simple for loop which goes through all the lights, which we've gotten reference to in a similar manner to as before, where we have, again, our library. We get access to all the data in this virtual scene, and we grab, in this case, both of the two lights that we have in our scene, and jitter them in this way. And I don't think it'll be quite as obvious as before, but I'll try and zoom in to show that. And you notice whenever I'm zooming in, I'm changing the orientation of the camera in the virtual world, and you can see there's a bit of this noise, and that's because this is real-time rendering. So this is, again, an advantage of these tools like Blender, Unity is they can do this very fast GPU accelerated rendering, which in this case is in the UI, but if we're generating our data set is done programmatically. So hopefully if I run this script, then you'll see that by changing the lighting parameters, you can even see that we're kind of capturing different shadows on the object to try and simulate what we'll run into in the real world in an object detection model. As before, another challenge being to make sure that you're setting these parameters correctly, because again, you want to get a data distribution that matches as closely as possible what you'll see on the real world. Will you have your headphones in a very dark room or a very bright room? You probably want to cover all bases, so to speak. But you can even see kind of the texture of the objects is really pretty good. You can even see, I think these are like threads, which are you could say it's overkill, or you could say that it generates photorealistic data. That's kind of a balance between the scene complexity and the time of rendering, but we won't touch on that too much. And then maybe one final randomization technique, with the caveat being all these are simplified cases. As you pointed out, you can get much more complex about this, but just showing you a few different ways is you could take the material of these headphones, and in Blender and in these other virtual environments, you can change different parameters about the shaders that ultimately determine how light interacts with the material. And if you want to see manually what that looks like, every object kind of has a description, a quantitative description of not only the color of the object, but also attributes like its roughness or its index of refraction, its emission strength, et cetera, all of which ultimately have bearing on the final rendering, on our final image data. And so you can also play around with different parameters there programmatically in our same Python script. So in this case, we're going to change the transmission of the material which is applied to the headphone object. As before, the library that we've imported, the data in the virtual environment, but in this case, instead of getting access to the objects in the scene, we're instead going to get access to the materials in the scene, and then randomize them in just one way here, but there are many different ways that you can randomize them, ways that might be realistic, might not be realistic. In this case, it seems to have a bit of a similar effect as changing just the lighting conditions. That's not necessarily the case. But every time we run this script, we get a different image. And we can pair that with all the other domain randomization techniques for every single image that we're generating. Right. And the final one being final randomization technique that we also touched on, which is a bit redundant with the first one in this particular case when you have one object as opposed to many, but changing the position and orientation of the object itself in the scene as opposed to the orientation of the camera looking at the object. And just for practice, similar approach as before, where we define a function which takes as input a single argument, which is one of these objects, in this case the headphones. And then we set certain randomization parameters, which we can then in our Python script apply to the object, scaling, location, and then rotation. If we change any of these parameters, we ultimately change the image data that we're getting out that will be used that we'll use to train the network, and so it is important. For instance, if I were to play this, then we're rotating the object, and I could go crazy with the scaling by changing these parameters, which will not be quite as good because sometimes, as you can see here, the data starts to look, like when would we ever have an image that looks like this? Maybe if someone took a very close-up shot of the headphones, but generally we want to match the data that we'll see in the wild. And so setting these, what you'd call them as, I suppose, hyperparameters, just like when you're training a network itself, you have certain hyperparameters which need to be tuned. In this case, unfortunately, as I'll touch on a bit at the end, tuning the hyperparameters of the data set generation synthetically can be a bit manual as well. Not quite as manual as generating the entire data set yourself manually, but there's some exciting research I'll touch on the end which seeks to automate even this process. Does that make sense at a high level? Any questions before I go back to the slides real quick? Has anyone ever used Blender before, just out of curiosity, or heard of it? Yes, yes. What context have you used it in? I'm curious.
I haven't used it, but my friend uses it to make models and physics.
Yeah. So it has physics-based modeling, and that's actually interesting too, because not only static images but videos, animations, you can also use for training data. In that case, while there's a lot of approximations that computer graphics engines like this make on the physics of an environment, particularly, for instance, for autonomous vehicles, having that sort of physics-based rendering animation can be very powerful. Yeah, absolutely. Anyone else used Blender before? Yeah, what have you used it for? I'm curious. Architecture modeling. Yeah, absolutely. Yeah, it's very powerful in how it kind of it integrates the modeling along with the rendering and the animation in a way that other tools don't, which makes it attractive for this task in particular as well. Yeah. Yeah, that's right. Yeah, conceptual modeling, that's right. Yeah. Anyone else? You all use it now though, right? Yeah. Okay. All right. So okay. So yeah, just walk through all this. I won't anymore. The scripting interface, and yeah, this is just summarizing what we just walked through in the demo, just the kind of a pseudocode form. This being a simplified version, but at a high level, what we're doing, what those companies are doing, is initializing a data set from scratch, and then iteratively, for one or maybe multiple different models that you want to detect in the scene, jittering their positions or orientations, deforming them, scaling them in different ways, their material textures, randomizing the lighting in the scene, the camera position and orientation, and then, as I'll show you in a second, annotating them. And that's maybe the most important part, is also annotating the bounding boxes of those objects in the scene, and then ultimately rendering them to the data set that we'll use for model training. Right. So this is, apologies for the bit of an unfortunate color scheme, but hopefully you can see that there's the image that we just saw, but then, as I just said, what's very important is getting this mask, this instance segmentation mask, which takes every image and black everywhere where the object is not, and blue everywhere the object is. For many images, of course. And from this instance segmentation mask, which is drawing a polygon around the object, you can also simplify that to just get the bounding box, as I'll show you in a second. Right. And so to show you what those bounding boxes look like, let's go to another bit of a demo. Let me close out these. All right. So this is just gonna. Now it's a bit. Is it too small again? Let me try and blow this up a bit. All right. So this might look a bit more familiar to you all. Or maybe it's dark theme, so not. But this being, we're back in a Jupyter notebook, and what we're going to do here is we're going to visualize some of this data that we've generated, check it, make sure that make sure that we have got our images in the correct format to train a neural network. There'll be a few libraries which maybe are unfamiliar to you, but are definitely not on the exam. But some that may be CV being for computer vision, so that's one we'll use. NumPy, Matplotlib for plotting. Some of these look familiar to you all. Have you used any of these in the course to date? Yeah. This one we won't really touch on most, but for the machine learning, scikit-learn has modules for doing some of the pre-processing that's important as well. Yeah, so let's see here where to start. So I think I'll start here. Just doing some pathfinding. We're pointing to the location on my computer where we saved all these renders. Saved all the images along with a file, a JSON file, which contains all the annotations. I can kind of show you what that looks like as well. So we have all these images, which I just showed you. But then along with the images, we have this file that, maybe I can actually just open it, that contains some metadata, but then the important part is down past all the metadata. Which is, may look a bit daunting, but at the end of the day, all this data is giving you is what is the ID of the object that we want to detect? What is its bounding box? That is, these are the 4 points in the image that correspond x, y, x, y, that correspond to the bottom left corner and the top right corner of the bounding box around the, in this case, headphones. And then the segmentation mask that is drawing exactly that polygon that outlines precisely, which would be very hard to do otherwise, where exactly the object is in the scene. And we won't be training a neural network to do that. We're doing YOLO, which is only bounding boxes, but that could be useful for other models as well. And doing that for a huge number of different objects, all of the, in this case, I think it was 500, but as you saw in that paper before, you could get up to hundreds of thousands of these objects relatively easily, but parallelizing and such. And you can even run it on the cloud as well. This is the data that we're working with, and we can visualize. So if I'm running these cells in the notebook here, I'm just loading that file that lists all of the data about the images, and so we have 500 images in this case. This printing the length of our data annotations, and maybe we want to inspect this data a bit. So this is just a little helper function that will take in those annotations and just find what is the maximum value. So we just iterate through the list, and we are looking at the ID of the image, and then returning what's the max of that. And so that gives us the maximum image ID. You all are using a different library for data frames, but this just being one to look at tabular data, where we have, again, the columns, which correspond to what image we're looking at, the class, which is the object that we're going to be detecting. In this simple example, we only had one class. We only had a headphone. So the classes are all going to be 0. But then we have these columns, which give us the bounding box coordinates. In this case, it's a bit of a different format than before. Instead of having the x, y position of the bottom left and the top right, instead we're just gonna look at the data where we have the lower left corner, but then we also have a width and a height of the bounding box, which tells us the same information. And essentially what this is doing is taking this data frame and populating it with all all that data that we imported from the JSON file, and then displaying it here. So for every, we have 500 rows in our data frame, which correspond to the 500 images, each of which has that same one class, the headphones. But then we have, for every image, we have a different bounding box, as we expect, with a different width and a different height, depending on the orientation of the camera, of course. Which is nice, because now we can work with that data more efficiently. This is just telling us what we already knew, which is if we want to know what are the unique values in this column, how many classes are we looking at? In this case, we're just looking at one. But of course, you could do this for different classes. If you wanted to differentiate between different headphones, you could. And I won't go into this. This is not super important, but this is doing some just massaging the data in the right format for training the YOLO model, adding a few columns, such as setting, again, the dimensions of an image that you need for training YOLO. Your data needs to be 640 by 480 pixels, and some helper functions to allow you to do that, getting the width of an image, the height, the center, and doing some normalization as well, just helper functions. So all this, again, is, as maybe you've realized from the course, is there's a lot of work that goes into processing the data to get into the right format that in this case, a neural network will expect. So the rendering is one part, but that second step is important as well, which we're doing here, where we're taking our data and then adding certain columns to it in the exact nomenclature that the model will expect, and applying those helper functions that we wrote before to do that. Ultimately, to get it into, this is again the same information, just we have different columns now that we need: width and height, x center and y center. Seems trivial, but all we've done is, before we had the bounding box described in one coordinate system with a lower left corner and then width and height, but YOLO expects there to be a center point and then a width and height. So we've just manipulated the data in the data frame to do that, but efficiently. And we didn't do this manually. And then dividing the images. We've been looking at the statistics of the bounding boxes, but also now we need to, and again, this is not about training a neural network, because that is one course, many courses, but getting the data in the right file organization to train the model with, which, as maybe you all have learned a bit about, you need a training data set, you need validation. This is where we've stored our renders from the virtual world to begin with, and we're going to just make the paths that we need to do that, using the OS library operating system. And again, whenever possible, not writing code ourselves, but using, in this case, functions from that scikit-learn library, which will automatically take your data, split it according to a certain division between training and validation. In this case, 90-10. So 90% of that synthetic data, and this is another important point, is the data that you should use to train the model should not be the same data that you use to evaluate the model. The same holds for synthetic data. So same principles as apply to working with real data apply here as well, using this function segregate data. Checking to make sure that we've done everything correctly, where we're just looking in this directory. In this case, we have a directory of images, so the RGB 640 by 480 images, and then the labels for each of those images, which is exactly what YOLO, the object detection model, expects. And we have 450 of the training images and 50 of the validation. And every single one of those images then has a label file corresponding to it. For a harder object detection task, we would probably need more images than this, but just for illustration. Um, does this workflow make sense to people? Sound familiar at all? Has anyone? I know that they've not done much machine learning training, right? A little bit. Anyone done stuff like this before? Pre-processing data for these object detection models? A little bit, yeah. What's the most frustrating part to you? Or is it easy? That's all right. That's also all right. Yeah, getting the data. Yeah. So, what sorts of data are you working with, or have you worked with?
Right now I'm working with Spotify API.
Oh.
So I'm classifying like happy versus sad playlists.
Ah.
But how I got the data was that Spotify, they have like these pre-made playlists. Like if you go in the search function for Spotify, they have like
Yeah.
happy playlist, sad playlist. So I use some of those songs as my training data.
Yeah. Oh, very cool. Very cool. How large was that data set?
Not too large because I just started the project. So I see
Yeah.
like around like 50 playlists so far.
Cool.
Each happy and sad.
Yeah. Yeah. Anyone else done any data pre-processing for machine learning in their day? I'm sure you all will. You all will. But anyway, this being the last little bit, which is actually visualizing what all this was for, which is using this library, OpenCV, Open Computer Vision, to take our, in this case, we're going to take an example image, and I think it might actually be not named properly. I have to get the path right. And I'll actually, just to make sure, go back here. So we've divided our data into images, and I'm going to take one of these images, maybe this one, and I'm going to visualize it. And actually, while I do this, how about we take a bit of a break? I will let you guys have a break. What is it? It is 11:05 already. Okay, let's take a quick 5-minute break, and then we'll finish up. Does that sound all right? Okay, cool. Yes. Okay, almost done, uh, but can't let you leave without showing you we've actually gotten the data in the format that you need to, for instance, detect your AirPods Max if you wanted to. So this being using that computer vision library, we're going to read in one of those images that we generated. And we're also going to read in the annotation file that describes where that bounding box should be, which is in a TXT format. Every PNG has a TXT associated with it. Just some helper functions to massage the data into the correct format, but we're going to go through all that data that we read in, and we're going to put a rectangle or a bounding box at those points on the image, and we're going to color them according to the class of the object that we're trying to detect, and then put that class, which is not really interesting in this scenario because we only have one object, one pair of headphones. But again, if we had a multi-class object detection network, then that'd be more interesting. And then show what that image looks like. So this being a kind of canonical example of iterating through a data frame and performing, in this case, our computer vision task. But ultimately, this is what we get. The dramatic finale. We have our image. We have the pair of headphones, and in this case, to return to the beginning of the lecture, remember what I was doing with that manual data annotation is I was taking this image and drawing that bounding box. Very exciting. But this just to show that for this image, it looks pretty good, not surprisingly. And we can do that for one test image, or we can do it for some other random image in our data set, just to show that for all these images that we've generated, we have a pretty good looking bounding box that surrounds where it is exactly in the scene. And then let's do one more. And hopefully you can see in the rendering that they all look different. Oh, that means that we don't have this image. That would be because, okay, so I've randomly selected these images, but actually, if you remember before, we divided our images into training and validation. And so I actually selected an image that we had not put in our training data set, but we had put in our validation data set. So that is why it was not found. I'm going to try randomly again, but because our train test split was 90-10, there's a pretty good chance that we get a training image, and there's another training image. So, any questions on that before I conclude with some? Yeah, sure.
Yeah, since computer graphics is not 100% replicative of the real world,
Yeah.
How well does this train in real time? I mean, how well does this test on real time? And is there any bias towards synthetic data?
Yes, and that is a great question because it is exactly what I was going to talk about. Synthetic to real gap. Yeah, so I think what you're touching on is what's referred to in the academic literature, well, by various names, sim to real, synthetic to real gap, which is, as you point out, and as these authors point out, often in these virtual environments, we start with CAD models, computer-aided design models, which are, in theory, perfect representations of what we're trying to detect. But then in the real world, they're not, of course. There's imperfections. There's lots of textures that we can't replicate. This is a bit of this is, I think, bashing on synthetic data a bit too much because it's implying that we're not rendering or doing any sort of texturing or material lighting. But regardless, yes, there will always be discrepancies between the synthetic data and the real data. One approach to trying to solve that is to try and make the graphics pipelines even more photorealistic, and try and make the data distributions match as closely as possible by, for instance, improving the way that you model how light is bouncing off of objects, etc. Increasingly, I think what researchers find is that a more promising avenue is actually to try to think about how we can, for instance, this is research from 2018, so a little bit dated, but using, for instance, GANs to try and identify, discriminate between real-looking and not real-looking synthetic images, for instance. This is kind of looking at exactly the pipeline that we were just demonstrating: synthetic labels, synthetic images, real images, but in this case, they're using a convolutional neural network. Along with, in this case, you have a discriminator. And this is definitely not the focus of this lecture, but trying to reduce that synthetic to real gap as much as possible. Where it seems like, in this paper, they're actually looking at feature maps and trying to align those feature maps between the synthetic image and the real image as closely as possible. But again, this is not my expertise and definitely not what we've looked at today. Does that start to answer your question a bit? Yeah. So there's lots of different approaches that people are pursuing. But I guess the main takeaway being that it's not just trying to make the images more realistic. It's also trying to more cleverly, like if you remember that image that I showed you at the beginning, it didn't really look at all photorealistic. Or it kind of looked photorealistic in the sense that the objects that we were looking at looked like cereal boxes. But the context in which they were positioned looked completely random, but trying to come up with those sorts of images that allow the model to identify features that are in the real world as well is even more important. So, any other questions before? I think I have one more slide, which definitely builds off of what we were just talking about, which is what if, ending with, of course, always with generative AI. But so we've just walked through this workflow of procedurally generating a virtual environment, which has the benefit of great control. That is, the designer, the modeler can tune every aspect of the scene, of the virtual scene, and the textures and the lightings and the camera, et cetera. But that's obviously very manual. That's very manual itself. Again, not as manual as labeling the data individually, but still takes time and expertise. So increasingly, either embedded within these graphics tools or externally, we're trying to think about can we reduce that manual effort as much as possible. And there's a kind of field of procedural modeling, which is coming up with, and this touches more on my research, algorithmic design, where you're trying to facilitate the very efficient generation of forms of models. Can you do that not only directly with the designer specifying, for instance, all the dimensions, but can you use generative AI to help with that as well? Trade-off again, though, between you start to lose control over the scene that you're generating, and the training of that network to generate the scene can also be, to a certain degree, challenging as well. So all these approaches have trade-offs, pros and cons. But collectively, I think they really promise to work towards that goal, that aim that Andrew Yang set out of data-centric AI, which is thinking about that 80% of the data preparation which goes into training an AI model as opposed to just the model itself. So anyway, I hope this was interesting, useful, maybe at some point in your career. But as I said before, please do reach out if you have any questions. I should have put my email. Let me put my email on here real quick. And you all will have access to these slides afterwards, which I've been informed by the TAs will be on the final exam. Will not be on the final exam. Want to do a vote? a quick Slido poll. Yeah, that's right. So anyway, any last questions? Any last questions? What's that? My axe? Oh, yeah, that's right. Who likes Berkeley more than Stanford? Who likes Stanford more than Berkeley? Yeah. Show of hands. Yeah. For sure, Berkeley. Okay. All right. Thank you all for your attention.